Okay. So my name is Aga Bialek, and I work in the UK in the National Physical Laboratory, and will tell you a little bit about what we do here in terms of sensing. So basically, just a quick overview. I will introduce myself in more detail and the organization where I work, and cover some basics of metrology, and then show you a few examples how we try to use it in remote sensing or air observation applications. So who I am? I'm a physicist by education. So I studied technical physics in Poland. And then I moved to the UK, where I started to work at MPL and did my PhD part-time at the same time as working. In terms of scientific interest, it's very much related to Earth observation, and in particular, quality assurance for Earth observation for the satellite sensors operating in optical domain. So it's very much the imaging satellites, and my particular specialization is in vicarious calibration and validations of those sensors via different test sites. So you can see the selection. So I run the site in Namibia, in Gobabeb, which is desert-based. I work with ocean color community, where we have measurements in water and above water, and we try to validate ocean color products. And very new to my test site portfolio is a vegetated sites. This one is in Whiteham Woods in the UK, where we basically we mount the spectrometer on top of the flax tower and basically want to measure reflectance. So all those measurements, which I do very much consider reflectance or radiance or irradiance. And my favorite unit and SI unit is candela though. So where I work at the MPL, which is the National Measurements Institute for the UK. So we maintain the base units, we disseminate the scale, but on top of it, we try to be the center for technology and science as well. And we are based in the suburbs of London. So the International System of Units, the SI, how we call it, basically was signed first back in end of 19th century in Paris, and it's basically the agreement to use the convention of the meter. So the countries who are signed to this basically agree to use the same system of units for their measurements. And at the current stage, we have 63 countries, which are the full members, and 40 associated states. If you want to know more, this is the website address, and this is the BIPM, because this comes from French, basically. So why this is important for everyday life? Basically, before that, every country could measure things in various different units, and it was started to be very hard to trade, and especially when we start to move towards some technological improvements, it started to be very difficult to communicate between different metric units. And there are some examples of really big issues when this is not maintained. So I don't know if you remember, a long time ago, the NASA Mars climate orbiter basically was lost because there was some misunderstanding between engineers. So the units from English old type units were not properly converted to metric units. So yeah, so the satellite got lost, for example. So in the heart of that 7 base units and the conversion of the meter is basically the definition of those primary units and dissemination of those to all sort of measurements across the world. And like you can see, there is a lot of regions and countries that are assigned to that SI system. And basically all measurements calibrations must be linked to the accepted national standards, and what we like to call via unbroken chain of calibrations, and preferably those calibrations should be carried out by an approved calibration laboratory. So we as NMIs, we maintain our scales and make sure that they are disseminated, but we cannot always provide calibration to all the people that they need them. So there is a set of accredited laboratories that they will maintain the scales as well, and they will disseminate it further. So what we want to ensure that basically we are compatible with all other institutes, and the measurements done, for example, in Europe is compatible with measurements done in Asia or Pacific region, and basically, yeah. So what is important for us is that scale realization is maintained over the time, so it's not changing. And we very much care as well about the evaluation of measurements uncertainties. And again, we have our main sort of document that define the methodology for uncertainty evaluation. And again, it's very much derived from that BIMP, which is called Guide to Expression of Uncertainty in Measurements. We like to call it GAM. And this is the link to those publications. There is several versions of that, but basically we like to express uncertainty based on the methodology described in the GAM. And that is very much maybe not always easy to digest. This is very much statistical language, and the examples there are very much related to not simple, but to the laboratory measurements. There is not a lot of linkage in the GAM to remote sensing, to applications that are taken in situ or to Earth observation. So that's why at MPL, we sort of created the Earth observation uncertainty training, which is basically trying to link the GAM to the Earth observation problems, and trying to find that linkage. So if any of you is interested, again, this is the link where you can access the training provided. And just a little bit about the GAM. So again, from the national measurements perspective, we know that basically each measurement will have some sort of uncertainty because none of them are perfect, and we never really know the true value of the measurement. So that uncertainty is defined as a non-negative parameter that will describe the spread of the possible measurement values. And again, in the GAM, we call it the law of propagation of uncertainties, which is very much defined by this equation, where the C components are called sensitivity coefficients, and there are basically the partial derivatives. And Xi elements are various inputs parameters into the measurement function. So this is the basic analytical method to calculate uncertainties, but over the time, and especially again for remote sensing, for Earth observation application, this can be very complicated to calculate everything analytically. So we tend to use Monte Carlo method more and more, which basically uses the statistical approach, where we define our measurements function as a number of inputs, but each input we define by its value and the probability distribution of each input. And then rather than calculate sensitivity coefficients for that function, we basically run the measurements many times, randomly drawing from each distribution to create the probability distribution of the output uncertainty. And so I would say that as NMI, we have like 3 different functions. We maintain the scale, we disseminate the scale, so we make sure that what we measure it's what it meant to be measured. We calculate uncertainty for those measurements because we believe that there is no measurements without uncertainty estimation. But as well, we need to validate that we are right. So we have to do comparisons. We have to compare between different NMIs and be sure that we agree each other. So we have to establish something which is what is called the degree of equivalence between the realization of different measurements. And that basically helps us to ensure that we do the correct job and that our uncertainty evaluation are right, that we don't underestimate or don't overestimate our uncertainties. And now how these principles can be applied to remote sensing. I think that several years ago, the initiative called Quality Assurance for Earth Observation was established, and they basically started to apply metrological aspects into the Earth observation. So in terms of the optical radiometric SI traceability scale, I think that this is a particular example for satellite ocean color, but it can be exactly the same scale dissemination for any radiance or irradiance measurements, not necessarily ocean related. So what is going on at the moment when we want to establish the scale? Our primary standard, which is on top of the scale, is cryogenic radiometer, which defines the optical power. And from that optical power, we can derive, using a trap detector responsivity. And having that, we are able to basically create the radiance responsivity. And then it's where, for the most in use traditional approach, is where we start to use black body, because black body is a very useful source for us. We can easily know its radiance basically using Planck's law. So it's where we use the black body. We use black body to calibrate the lamps, which are a source of our irradiance, and integrating spheres that are source for radiance, basically for us. And those two are mainly used as the absolute calibration standards. If we want to if you want to derive the radiance source using irradiance lamp and the reflectance standard, we have to derive reflectance from a separate scale. It's not the same as optical radiometric scale. We have a reflectance scale where we calculate the reflectance factor and, for example, calibrate spectral panels. And then calibrated spectral panel together with this calibrated lamp will give us a radiance source as well. And what is very important for application related to field and in situ, it's when we do absolute calibration of the radiometers, we have to really repeat it on a regular basis. So we have some initial calibration. We might have some period of times when that instrument then is used in situ or for the campaign or for some period of deployment. We have to do regular recalibration to check its stability and basically correct for any drift in the instrument. So it's very important for us to do it in that loop and to maintain all the records and know what is changing in the instrument. And only what we like to say, that only when we have that secondary recalibration after the deployment, we are able to provide the product that will be useful for calibration or validation of satellite sensors. And in terms of SI traceability, again, when we start to apply it for in situ application, in terms of reflectance scale, it's a little bit complicated, because with that reflectance, there is a little bit of mismatch what we can do in the laboratory condition and what is really happening outside. So this is the example of various different illumination and viewing conditions for reflectance measurements. So basically the simplest one is bidirectional, when we have directional illumination and directional viewing, which is very much what we try to achieve in the laboratory conditions, but it's definitely not what is happening when we take instruments outside and when we measure. So that's why what we propose, for example, at MPL, for any measurements that are traceable to reflectance via spectral calibration, to really make sure that we don't use only the typical calibration value from which is very much defined as directional illumination and hemispherical viewing, which is the most common what we can get from LabSphere when we buy a Spectralon. We should look a little bit more and try to know really the BRDF of that panel, which will be the directional to directional illumination, and vary it with our solar illumination during the measurement. So for example, that BRDF of the panel will change depending if our solar zenith angle is 20 degrees or 30 or 40. And there will be always a split between that amount of the downwelling irradiance in situ. We will have some amount which is really attributed to the direct sun, and that is the amount of the reflectance very much related to BRF properties of the panel. And the rest, which is related to diffuse sky radiance, and this very much we can refer to that hemispherical component that is we can call total diffuse reflectance as well. And I believe that we really work hard in MPL to start to basically distinguish those two components and try to apply it in some of our measurements.
Just 2 more minutes.
Yeah. Okay. Ooh. Okay. Thank you. So basically, yeah, this is what we propose, and this is for example the difference that we can see for some again measurements over GOBABEP. We have different proportion of direct solar illumination, and obviously it's changing with the wavelength scale, and we can see what is the difference between using the what we call HDRF method to calculate ground reflectance versus BRDF. And for some wavelengths, we can have difference up to 1.6% or something like that. If we want to have very accurate in situ measurements, we should really try to eliminate the source of uncertainty, which is related to wrongly applied spectral panel calibration. So for our work, we use mostly radiometers, and again, we can have multispectral radiometers, which are stable and reliable, but they give us limited information. And the world went hyperspectral, where we have full information about spectrum of interest, and we really use a lot of hyperspectral instruments, but they really are more demanding in terms of characterization, especially when we take them outside the lab. And basically, it's what we again work with our partners, we try to establish as many instrument characterization as possible to apply correction for those measurements when instrument is taken outside of the lab. And there are some examples. For example, this is a temporal responsivity of some of the again, hyperspectral instruments, and it's really changing for some sort of wavelengths. And if we don't apply that correction, the absolute calibration coefficient that was established in the lab at one temperature will be not applicable anymore. We have a spectral stray light in those types of instruments and detector linearity response, which really vary with the flux levels. So if we use spectrometers really to have accurate measurements and estimate the uncertainty, we really recommend the full characterization of those instruments and apply correction coefficients using them outside the laboratory conditions. And this is another example of work. We sort of work with in situ application and at Earth observation and remote sensing, and we think that basically GAM is not fully covering everything what we need to cover. And there is something which we call fiducio approach, which try to adapt uncertainty evaluation to remote sensing needs. And what we present here is uncertainty tree diagram, which basically split the one measurements of radiance, and again, this is an example of water leaving radiance, into all basic components, and everything what goes into that equation basically is presented on one screenshot when we go from instrument digital numbers via calibration, characterizations, corrections with all uncertainty contributors into the spectral convolution. And we even touch on some of the modeling errors and related to models of calculating, for example, here Fresnel reflections. So this approach, it's basically allows us to capture everything what needs to go into the calculation of uncertainties. I think we use it quite a lot now. So when we want to calculate uncertainty in situ, we first sit and draw it to make sure that we capture everything. And again, we work with various community, and we encourage them to do those comparison, how the NMIs will do. So in ocean color community, we defined something which is called fiduciary reference measurements for satellite ocean color radiometry. And we had several participants, they wanted to basically to participate in comparison how NMIs do it to establish basically some sort of agreement between their measurements. We run those comparison in the lab and in situ. In the lab were obviously a little bit easier, but still in the lab for irradiance, we didn't see many problems. It seems to be easier, but our radiance comparison shown that we had several participants with uncertainty much higher than expected. So we would expect to have radiance uncertainty at around 2.5 to 3%, but some of the participants had basically results much more different from the main group. And then we came back, we revisit the methods, we revisit the problems and try to, and basically came up with some solutions. So in this case, there were people who were using too small illumination size on the radiance measurements, and they could basically not properly fulfill the field of view of the instruments. That's why they were so much off. And we try to apply those across the various networks. So this is the two examples of the radiometric networks that are currently, one is established for some time, which is RadCalNet, where we have the test sites, and they're really very much run on the basis of providing measurements with uncertainties, and they are then used for satellite comparison, again with uncertainties. And HyperNet is a network that we are currently established, which is very much in the same sort of spirit to provide measurements with uncertainties. And I believe that it's everything from me. Thank you very much.